All right, welcome. Today we are talking all about light, and we're going to see how two of its most basic behaviors, the way it bounces and the way it bends, all come down to a single, unbelievably simple rule. So think about this for a second. How does a beam of light know the absolute quickest way to get from point A to point B, even if it has to bounce off a mirror to get there? It's kind of a weird question, right? It almost sounds like light is thinking. Well, the answer is found in one incredibly powerful idea. And here it is. This is our master key for today. It's called Fermat's Principle, or the principle of least time. All it says is that out of all the possible ways light could travel, it always takes the path that gets it there the fastest. That's it. This one idea is going to unlock everything else we're about to explore. Okay, so let's put our new rule to the test. First up, reflection. You know, when light hits a mirror. How does light use the least time rule to figure out exactly how to bounce? This image shows the problem perfectly. Let's say light leaves point A, and it has to bounce off that mirror to get to point B. I mean, it could hit the mirror anywhere along its surface, right? But it doesn't. It hits one and only one specific spot, point P, because that is the single point that makes the total travel time as short as it can possibly be. So how do you find that magic spot? Well, mathematically, you'd start by writing an equation for the total travel time from A to P to B. Then, you'd use a little bit of calculus to find the one point where that time is at its absolute minimum. And when you solve that, what pops out isn't just some random number, it's a fundamental law of the universe. And this is it. It turns out the path of least time always happens when the angle the light comes in at is exactly equal to the angle it bounces off at. The angle of incidence equals the angle of reflection. This isn't just some rule someone made up, it's a direct result of light being incredibly efficient. Okay, so to make sure we're all on the same page, let's quickly define these terms. The incoming light is the incident ray. The light that bounces off is the reflected ray. Now, the most important one here is the normal. It's just an imaginary line that we draw, sticking straight out from the mirror, at 90 degrees, right at the point where the light hits. Both angles are always measured from that line. Now that we've got this law, angle in equals angle out, let's see what happens when we apply it to different kinds of surfaces. We're talking smooth mirrors, rough roads, and even mirrors that are curved. So when light hits a super smooth surface, think of glass or perfectly still water, you get what we call specular reflection. Because the surface is so flat, all the parallel rays of light come in at the same angle, and so they all bounce off at the same angle too. They stay together in a nice, neat bundle, and that is what lets you see a clear image. But, you know, most things aren't perfectly smooth. A piece of paper, your shirt, a wall, they're all rough on a microscopic level. So when parallel light rays hit a surface like this, each ray hits a tiny little patch that's facing a slightly different direction. And here's the cool part. Every single one of those rays still perfectly obeys the law of reflection. But because the surface is all jumbled, the rays scatter in every direction. That's diffuse reflection. And this just makes the difference crystal clear. Specular is from a smooth surface, it keeps the rays parallel, and forms a nice sharp image. Diffuse is from a rough surface. It scatters the rays and doesn't form an image at all. It's why you can see yourself in a mirror, but not in a wall. Okay, here's a fantastic real-world example of this. You've definitely experienced this. A dry road is rough, right? So it reflects light diffusely, scattering it. But when it rains, that water fills in all the tiny little pits and cracks, making the surface smooth. All of a sudden, you've gone from diffuse to specular reflection, and that's why the headlights from oncoming cars create that intense, dangerous glare. So far, we've only been talking about flat or plane mirrors, but things get really interesting when we start to curve the surface. And there are really two main ways to do this. You can curve it inward, which we call concave, or you can have it bulge outward, which is convex. So a concave mirror, which is shaped kind of like the inside of a bowl, takes all those parallel light rays and brings them together, or converges them, to a single spot called the focal point. A convex mirror does the exact opposite. It spreads the light rays out, it diverges them, and makes them look like they're coming from a point behind the mirror. And that diverging property of convex mirrors is incredibly useful. Just think about the side view mirror on a car. It's a convex mirror. The image you see is always upright, it's always smaller than the real object, and it's virtual, which just means it appears to be behind the mirror. This gives you a much wider view of the road, which is also why they have that warning. Objects in mirror are closer than they appear.
All right, we have totally figured out reflection. But what happens when light doesn't bounce? What about when it goes from one material into another, say from air into water, and it bends? Well, this is called refraction. And you guessed it, Fermat's principle explains this too.
So take a look at this setup. We have a ray of light going from point A in a fast medium, like air, to point B in a slower medium, like water. Now, here's the absolute key. The speed of light changes when it crosses that boundary. So how does it find the fastest path now? Well, to save total time, light does something really clever. It decides to travel a little bit farther in the fast medium, the air, so it can spend less time in the slow medium, the water. Think of it like a lifeguard on a beach. She can run way faster on the sand than she can swim. So to reach a swimmer in the shortest time, she won't run in a straight line. She'll run further down the beach before jumping in the water. Light does the exact same thing. And when you do the calculus to find that optimal lifeguard path for light, you get another legendary law of physics, Snell's law. It's a beautiful little equation that tells you exactly how much the light will bend based on the properties of the two materials. And again, this whole thing comes directly from that one simple idea. Light always takes the fastest route. Okay, let's step back and pull all of this together. We've talked about reflection, refraction, curved mirrors, rough surfaces, the whole shebang. So what's the big unifying idea here? We end up right back where we started. This one simple, elegant sentence. From a perfect reflection in a mirror to the way a straw looks bent in a glass of water, it's all of it, governed by this deep principle of efficiency. So if you remember one thing, make it this. The law of reflection and Snell's law of refraction, they aren't two separate rules. They are just two different results of the exact same deeper principle. They're two sides of the same coin, and that coin is nature's incredible tendency to find the most efficient way of doing things. And that really leaves us with a mind-bending final thought. This idea, sometimes called the principle of least action, shows up everywhere in physics, from the orbits of planets to the bizarre world of quantum mechanics. It just makes you wonder, if light has figured out this ultimate shortcut, what other amazing efficiencies are hiding in plain sight all around us?